Okay, what we're going to do now is calculate the chi-square test statistic. We're going to use example problem 4 on page 201. It blends from page 201 to 202. And what the exercise as you look at is the proportion of people whose draft number falls within a particular range. That is, whether it's a high number, a medium level number, a low number in connection with somebody's birth month. And you could see here, this is the data just basically recreated from the book. So 2 questions might be, do people born in later months of the year have relatively high or low draft numbers? And these are draft numbers from the Vietnam War. How about people in earlier months? Is there a correlation? So notice, for one, that these data are proportions. So you're looking at the proportion of people, that is, if we broke each one of these out, they're percentages of a total number, and what number they actually had and when they were born. These are not means. So we're not getting an average here, we're getting a proportion. So in this cell would be 21 divided by 91, which is whatever, 25% we'll say. This would be 28 divided by 91. So again, a percentage of the total number of people within a particular group. So what you're actually looking at with a chi-square test statistic is, what is the level of deviation between what you would expect to get if things were done randomly versus what you actually, quote, got. So here's what you got here, and specifically what you got are these numbers in here. So for example, the number of people who, out of 91 respondents, who were born in January through March and had low draft numbers were 21. The number of people with high draft numbers was 36. So now what you want to do is figure out, well, if these numbers were randomly generated, what would you have expected to get here, and how different is what you got from what you would have expected? Because as you would imagine, the farther or the bigger the deviation between what you would have expected randomly and what you got, the less likely it's due to chance, and thus that there are real differences in proportions. Okay, so what you're looking at here is, now we're going to take you to what you might have expected to get just randomly. So the best place to start from my perspective is by removing all of the data above and just having the big picture sample data. So we took out all the actual numbers. So what we have left here are just information about respondents generally collected. So for example, we know that the number of people, respondents in total, was 366. We also know that 122 of them had low draft numbers. We know 122 had medium level draft numbers, and the number of people who had high draft numbers is 122. We also know that the number of people surveyed who were born between January and March is 91, and so forth down here. So by a good starting point to thinking about this is to just get a percentage here, turn it into a percentage, the number of people who had draft numbers in each category. So you can see it's equal here. The number of people who had low draft numbers out of those respondents was 33% of the total, 366. So now, if we just had this data, we didn't know what was actually came out of the data, what would we have randomly expected here? So all you need to do is multiply the number of people from each birth category times the percentage that you would have expected to get in each one of these cells. So let me give you a further example here. So if we know that out of 366 respondents, the percentage of people who got low draft numbers was 33%. Then naturally, if we had 91 people who were born in January to March, we would have expected randomly that 33% of them would have had low draft numbers. So 91 times 33% is 30.303. And you could see that below as I fill it in. Now, given these numbers are the same, when you multiply 91 times 33%, you're going to get the same number again. Okay, and clearly this number is exactly the same here, so you're going to get the same number. Okay, now if you were to look at July through September, if we know there were 92 people who were born during that quarter, and we know that in general 33% of those surveyed had draft numbers, we would multiply 92 times 33% and get 30.636. We would have assumed or expected that by random chance, 33% of the people in that quarter would have had low numbers, medium numbers, and high numbers. So you can fill in that data here. Now, here is the actual, again, recreated, so we can make that comparison here. So you can see just by looking, for example, that what we would have expected would be that if you were born between January and March, the likelihood that if 366 people were surveyed, 30 of them would have had low draft numbers. 30 would have had medium, moderately high level draft numbers, and 30 would have had high draft numbers. What we got was 21, 34, and 36. So for example, just by looking at the comparison here, we can see there's actually a good degree of difference. On the flip side, if you were born, for the people who were born between October and December, we would have expected that 30 of them would have had low numbers. What we actually got was 38. So it seems like there might be a difference. So this statistic examines how far away what you would expect is from what is actually there. And this is just a reiteration of what I just said. So the test statistic is, and I should add something in here, each of the numbers in yellow, that is each of these numbers, minus the corresponding number in orange. So for example, this one minus this one, squared, and it would be divided by what you would expect, and all totaled. So notice there will be actually 12 mini calculations that you would do. For each one of these, you would subtract, in this case, 30 minus 21, square that number, and divide it as a proportion of what you would have expected. So it's right down here. So 30.303 minus 21 squared divided by 30.03. Now what's interesting is, notice that this number, here's what that comes out to. 86.54 divided by 30.303. So it's essentially 9, 30 minus 21 is roughly 9, squared is 81. It's a little bit different. Squared divided by 30.303. Now, what if this number, the difference between what you would have expected and what you got, was much lower? So it was very close. So if it were 30.303 minus 30, the number that you would square would be much smaller, and thus as a percentage of what you would have expected would be much smaller. So this number would be more like, 1 divided by 30.303. And when you added it all up, you would get a much smaller statistic. So the bigger the differences between what you would have expected and what you got, the bigger your actual number that's totaled actually is. So for each one of these, I created the statistic for you. So let me go through with at least the second one. So you do the first one, here's the second one. 30.303 minus 28, so right here, squared divided by 30.303. Because you're trying to figure out, as a percentage, what is the difference between the two? Is it big, in which case there's more variance and a greater likelihood that there's a true difference between what's actual and what's expected? Or if it's super small as a percentage, there really probably aren't any differences that we could see. So you'd go through, and here's the last one. 17, what you actually got, minus, here we go. 30.636. And by the way, I reversed these. You could do these in either case because you square them. So I started in this case with the actual again. 17 minus 30, 6.6 squared divided by 36.6 as a percentage. And what you then get, I continue to draw this out for you, you total them, and you get 20.6. Now, I wrote in here Excel, unfortunately doesn't allow you to calculate the chi-square statistic. That's too bad. But if you were serious about this, you could get SPSS, or I believe it's called SAS. Now, 20.6, what the corresponding p-value for this statistic for 20.6 is 0.0021, which is a very small type 1 error. So you would reject the null because the p-value is so low, there's very little risk that if you rejected the null, you'd be wrong because the null was actually true. So evidence exists of differences in proportions. And in this case, specifically, it appears that men and women who were born between January and June were more likely to have higher numbers. So look here, there's 36 and 41 versus 21 to 28 right there. And people who were born in later months of the year tended to have lower numbers, 35 plus 38 versus 28 plus 17. So you conclude there is a relationship just by going back to look at the data between the two. Now, just to be sure, the critical value is 12 of the F. If you remember, you know what, I'm actually going to not add this in here for you right here. I'll show this to you later. Okay. No, maybe I will. Okay. So let me just make sure I got this right. Yeah, okay. So I put this in here wrong. This should be, I'm going to put in X. As you guys know, X squared is the chi-square number. So remember we talked about the critical value in during the sessions, which is essentially the number that represents the point at which you would reject the null hypothesis. That's what determines the critical region and the area of rejection and non-rejection. So I'm just sharing with you for the calculation people in the group. If you look on page 321, what this shows you is that the critical value in light of your level of significance and corresponding degrees of freedom. So on page 321, if you look under 0.05, and that's the column third from the left, and go down 6 degrees of freedom in this particular case, you would find the statistic 12.592, and that represents if the number, the chi-square test statistic, is higher than that, then you would reject the null hypothesis. Remember, we talked about that there are two ways, really, that you can determine whether to reject the null. One is by looking at the p-value, which, frankly, that's enough. Anybody who knows that knows enough. But for those of you who want more detail, you can also, according to the book, reject on the basis of the critical value and whether the test statistic in this case exceeds it. 20.6 exceeds 12.59, and as a consequence, you can reject the null. And to be sure, you get 6 degrees of freedom by subtracting 1 minus the total number of rows or columns in this case. So it's 4 minus 1, 3 times the number of columns here. So 4 minus 1 is 3, and rows, 3 minus 1 is 2, so 3 times 2 is 6. That's how you get your 6 degrees of freedom. I hope this helps, and I'll move on to another one.